Hello everyone, welcome to a fresh new lecture on the topic Filter Structures 2. This is Dr. Anirban Dasgupta and let's get started. So, we have already covered the structures for FIR filters and now we will look at the structures of IIR filters. And specifically we will study these structures, the direct form 1, the direct form 2, the transposed form 1, the transposed form 2, cascade form, parallel form and lattice ladder forms. So, we have already seen that an FIR filter in the Z domain is nothing but a polynomial in Z inverse. What about the IIR filter? So, IIR filter can be represented as a ratio of two polynomials in Z inverse. The first is NZ, that is the numerator part, and the second is DZ, that is the denominator part. Now, simply NZ can be written as one transfer function H1Z or one filter, and DZ can be written as another filter which is H2Z. Now, why I am doing this is because we can see that H1Z is consisting of the zeros of the filter HZN, whereas H2Z is consisting of the poles of HZN. So, in other words, H1Z is a polynomial in Z inverse, which is basically an FIR filter, whereas H2Z is a polynomial, is not a polynomial, it is inverse of a polynomial of Z inverse, or it is basically an all pole filter. So, hence that is clearly shown that H1Z is an FIR filter, whereas H2Z is an all pole system. So, now we can see that since they are multiplied in the Z domain, you can actually cascade these two filters H1Z and H2Z, or in other words, our IIR filter is a cascade of an FIR part and an all pole part. Now, based on which comes first, whether I put H1 first after H2 or H2 comes like after H1, we can get two such structures, and these are called the direct form structures. Why direct form? Because we directly obtain them from the transfer function without doing any manipulation or simplification. So, in direct form 1, what we do is basically, so we have this filter which is defined by this difference equation. Now, in this case, you can see that this filter YZ is basically some combination of present input and some past values of input, and this is the FIR system. And this is an all pole system where we have the previous values of output. This is kind of a recursion. So, this is a structure which is a direct form 1, where I have first the FIR system and then we have the all pole system. Now, here you see that, so this FIR structure, if you see, so this xn comes here and then this is multiplied by 3. So, this becomes 3 times xn, and then this is xn minus 1 after this delay, and which is multiplied by 5. So, this part becomes 5x of n minus 1, and then this is 7x of n minus 2, and this all gets added to make the output of the FIR system, and this is again added to the yn. Now, yn is again delayed. So, I get yn minus 1, which is multiplied by 6 here. So, this is 6 yn minus 1, and this is basically twice yn minus 2, and all these are added together to form my yn, which is this difference equation. So, here we have m plus n plus 1 multipliers. What is m? M is basically the highest lag in the FIR system. What is n? n is the highest lag in the all pole system. So, here in this case my highest lag in the FIR system is 2, and so m is 2 here, n is also 2 here. So, m plus n is 4 plus 1 is 5. So, we have 5 multipliers 1, 2, 3, 4 and 5. That extra one is for the x n without any delays. Adders are m plus n. So, these are the adders, and delays are also m plus n. These are the 4 delays. Now, the next structure can be done if we place the all pole filter first and then the all zero filter in this manner. So, what is the advantage I get here? I can combine the delays. So, this is very much similar to the direct form 1 structure in terms of multipliers and adders, but delays are being shared. So, if there was one more branch here in the output side or even in the input side, so we had to use one more delay. So, in general it is the max of m and n. So, whichever is having the highest number of delays, that is the number of delays in your direct form 2 structure. Okay. So, next is the transposed form, and this is come from the concept of signal flow graph, and in this transposed form we will use the same difference equation, and what changes we will do to the direct form 1 is that first is we will interchange the input and output, next is we will reverse all the directions, and third is we will interchange the adders and the branching elements and vice versa. So, if you see here initially, if you quickly see the direct form 1, so this is the direct form 1. So, here you see this is the input, this is the output. So, here y will come, here x will come. Second is the directions will get reversed, and third is the adders will be replaced to branching elements, like adders will go here and then branching elements will come here. So, they will change their place. So, this is basically the transpose structure of my direct form 1, and again if you verify we get the same thing. So, just do a quick verification. So, here I have written just an intermediate signal V of n, which is showing that this is the signal in between the cascades. So, if you use this V of n, it is easier to do the analysis, otherwise you still will come up with the same results. And needless to say, the transposed form true will be just the transposed version of the direct form 2, where we do these operations to the direct form 2 structure. So, now we have studied 4 structures for the IIR system. Now, let us look at the cascade form of the IIR, and which is very much similar to the cascade form for the FIR. So, suppose you have a big transfer function h of z, and this h of z can be factored into lot of such filters. I say hk of z, where k varies from 0 to n minus 1, which means there are n cascades like this, h0 to h of n minus 1. So, such a filter, and each is an IIR filter of smaller order, maybe 1 or 2. So, in this manner you can actually form different such small IIR filters. So, this big h of z, which is a huge filter of very high order, is broken down into small filters which are also IIR. Typically IIR, there may be one FIR also, that is not a big problem, but typically they are in cascades. So, what about the next form? The next form is basically the parallel form. So, what about the parallel form? So, parallel, as we know that what is parallel? So, in cascades are basically sequential or series forms. So, here one block is entering the signal for processing, and then the output of the first block is going to the second block, and so on. So, things are actually not happening so fast as it looks, because there will be lags while each stage is doing the processing. So, what about parallel? So, in our signal processing architectures also we learned that if we do some kind of parallelism in the architecture, in the operations, then things are faster. So, that brings us to the parallel form. Now, the question is that, so here if we see, so I have this expression of h of z. Now, in cascade forms, what did we get? The cascades were products of different h of z's, right? But in parallel form, typically what we get is they have to be sum of some terms. Like if you see this equation, h of z can be expressed as some constant and some sum of h of z's, which I say that h1z, h2z, h3z up to hn z, and then there is a constant which is just a simple multiplier, and then here everything is added. So, these operations are happening in parallel and hence they are faster. Now, what is the most important thing here is that typically these pKs are our poles. Now, the question is that if I am given an h of z, how do I break it down into sums? Well, the answer to the problem is that, so I hope most of you or maybe all of you have done this concept of partial fraction expansion. So, partial fraction expansion means you have to divide a big polynomial into some of its factors, and this is what I have done. So, if they are divided, like in say I have one h of z which is say something of a by 1 minus z inverse into b. Now, this can be polynomials of z as well, say 1 minus 2 z inverse. So, this is basically our cascade form, right. Now, in parallel form, what we need to do is we will get something c z 1 minus or c 0 1 minus z inverse plus c 1 1 minus 2 z inverse plus some c 2. So, this is basically the partial fraction expansion for this cascade form. And now, there are methods to obtain these values c 0, c 1, c 2, and this again may not be just constants, they may be c z inverse plus some d, something like that. So, now the question is that how can you get them? So, there is or there are rules to solve these equations to obtain the coefficients of the partial fraction expansion. Now, typically what I was saying is that, so in this cascade form, so what are these coefficients or values giving? These are basically giving you the poles, because say in this case the pole is at 1, the pole is at z equals to 2, and how do you know? Because at the pole this term becomes 0. So, hence the partial fraction expansion, if you know the poles, this is a very easy way to factorize by giving the poles directly here, and what you finally get is a parallel bank of single pole filters. So, this is one example where we have a bank of 3 such IIR filters. Now, so far the direct form was there in the FIR case, direct form, we got 2 direct forms in the IIR case, because there are cascades of an FIR and an all pole, and by the interchange of these filters we get 2 direct forms. Again similarly, by changing these branchings we got the transposed form. Cascade form also was there in the FIR system, and in the IIR also we got the cascade form. We are studying something new as the parallel form in the IIR case, but is there a parallel form possible for the FIR? Well, technically if you see, like here, since there are products and there is a denominator, and that is why you are able to break them into this partial fraction. But IIR, that is the IIR case, but in the FIR case, so if I have my h of z and if I want to represent it as sum of 2, it is nothing new, this is the same FIR filter only, because since there are no denominators, so like say if I have a polynomial in Z, so if you just break this as one filter and this as one filter, or this as one, this as one, it doesn't really change, meaning that the direct form realization of the FIR filter is already a parallel implementation, and as such there is no separate parallel form for the FIR filter. Now coming to the last structure, which is the lattice ladder form. So to deal with this filter or this form, let us begin with an all pole system with system function h of z is given as this. Now technically this is an all pole filter, as I said, so it has only the denominator part as a polynomial in Z inverse. And if you carefully look at the denominator, this is very much similar to the lattice structure of the FIR. So how do I use this information? Well, this is the filter in the time domain or difference equation, correct? Now what will I do is, if I carefully examine the structure of this filter, and if we interchange the role of input and output, that is make yn as xn and xn as yn, what do we see? We see that we get this expression, and this is what? This is our FIR filter, because yn is dependent on xn and our previous values of our xn. And we have already studied the lattice form for this FIR structure, right? So which means this all pole filter is having a lattice structure which is very much similar to the FIR filter. Just one condition, that the roles of input and outputs are changed. So this is what I am getting. So here the roles are basically changed, and here what we are getting is that, so this is the output is being fed back. So there is a reverse direction. So here you see that this K1, K2 and this Kn, these are computed exactly like the lattice structure of the FIR form. Only thing is that the output is fed here instead of the input. So it is going in the backward direction, and the remaining things are exactly the same. So this is basically what we were getting. Now again let us recall that the IIR system is a cascade of an FIR filter, this is the FIR, and this is the all pole. I can say FIR as all zero filter also, not a big deal. And in direct form 1, what we did is that, so first we did the all pole filter, and then we cascaded the FIR version of the filter, and we got a structure which we have already seen. Now here in the lattice ladder form, what happens is we have done the lattice, and what do we get in the lattice? We got the all pole version, and with the all pole we now need to cascade the FIR part, and this FIR part we can just use the direct form to realization, which is basically this part. So this is the lattice part, and this is the thing which is a direct form to realization of the FIR part. And if you look at this, this is looking like a ladder, and hence this is called a lattice ladder form or lattice ladder realization of the IIR filter. So you carefully see that this is very simple actually, although it looks very complicated. So if you are given an IIR filter, first you look at the lattice part, which is basically the all pole part. So if you are well equipped with the concepts of this lattice filter for FIR, then this is the same thing. This is exactly the same thing, just treating the output as input and vice versa. And the remaining part is just the direct form implementation, which is the FIR part, and this is basically your lattice ladder realization. So thank you very much. We will meet again. Have a nice day.